Welcome curious minds and sleepy thinkers. You've found a soft place to land, a quiet corner of the cosmos where the questions are vast and the pace is slow enough not to jolt you from your pillow cocoon. Tonight, we're going to gently drift into the silent embrace of a distant world, a sphere of ice and mystery that orbits a ringed giant far, far away. We're going to softly explore Rhea, Saturn's second largest moon, a place that, while often overshadowed by its more famous sibling, Titan, holds its own profound secrets and wonders waiting to be unveiled in the quiet of your thoughts. Imagine, if you will, the deepest quiet of a night sky so dark that the stars seem to pop from the velvet blackness, not as pinpricks of light, but as luminous dust scattered by a cosmic hand. In this boundless expanse, our own solar system shines like a luminous island, a tranquil harbor within the immense, silent ocean of space. At its heart burns our sun, a familiar warmth, and orbiting it are planets, each a unique jewel in a celestial necklace. Among these, Saturn stands out, a majestic ringed giant, its beauty so profound that it has captivated human imagination for centuries, a silent, swirling masterpiece of gravity and light. And circling this grand ethereal sphere among a myriad of other moons is Rhea. Rhea is not the largest, nor the most volcanically active, nor the one with a thick Earth-like atmosphere. It is in many ways a quiet world, a gentle presence in the bustling Saturnian system, a moon of quiet dignity. Yet beneath its seemingly placid surface, it harbors secrets as deep as any ocean and wonders as high as any mountain. We will speak of ice cliffs that rise hundreds of meters into the cold, distant sky, silent sentinels carved by forces we are only just beginning to understand, like ancient frozen cathedrals. We will ponder an internal structure that seems to defy our current scientific models, a core that whispers of complexities hidden beneath layers of frozen water. Like a heart beating softly within a shell of ice, its rhythm a cosmic secret. And then there is the enigmatic discovery, a subtle hint of something unexpected, something equally as strange as the very thing we didn't find, a cosmic paradox that invites us to simply wonder, to let our thoughts unfurl like sails on a calm sea, carried by the gentle breeze of curiosity. Tonight, we invite this lesser-known moon to step out from its larger sibling's shadow, to share its quiet stories with us. This isn't a race through equations or a lecture filled with facts to memorize. No, this is more like floating through a galaxy of ideas with a cup of chamomile tea in hand, allowing our minds to gently expand, to touch the edges of cosmic beauty and mystery without haste. We'll take our time like a slow-moving cloud drifting lazily across a summer sky, allowing each thought to settle, each image to form in the soft landscape of your imagination, painting pictures of distant worlds in the theater of your mind. Think of Rhea as a quiet library, its shelves filled with ancient books, each page a testament to cosmic time patiently waiting to be opened. We are merely turning the pages, not rushing to the end, but savoring each word, each illustration, each quiet revelation. This journey is about nurturing a sense of wonder, about finding peace in the vastness, and about understanding that even the most distant, seemingly ordinary worlds hold extraordinary tales. So let your breath slow, let your thoughts soften, and let us embark on this gentle voyage to Rhea, the silent keeper of secrets in Saturn's grand embrace. We will explore what scientists have discovered there, not with the urgency of a mission, but with the quiet curiosity of a dreamer seeking to discover its wonders for ourselves, allowing each piece of knowledge to settle like soft moonlight in your mind, illuminating the corners of your understanding. The very act of turning our attention to such a distant, serene object can be a profound balm for the soul. In a world often filled with noise and haste, there is a deep comfort in contemplating something so far away, so untouched by our daily concerns, yet so intimately connected to the grand tapestry of the universe we inhabit. Rhea, with its quiet dignity, reminds us of the endless possibilities that lie beyond our immediate grasp and the beauty that exists in the silent ongoing dance of celestial bodies. It is a world that invites introspection, a gentle mirror reflecting our own capacity for awe, for dreaming, for connecting with something larger than ourselves, a connection that transcends the mundane and touches upon the sublime. As we begin this exploration, let us first settle into the feeling of peaceful anticipation. Imagine yourself gently floating, suspended in the vast quietness of space, the distant stars twinkling like scattered diamonds against a boundless velvet cloth. Below you, the earth of vibrant blue marble slowly recedes, becoming a smaller and smaller point of light, a fading memory of bustling life. You are moving outward towards the cool, dark frontier of our solar system, past the fiery embrace of the sun, past the rocky inner planets, and into the majestic realm of the gas giants, where gravity weaves its most intricate dances, pulling countless moons into its graceful orbit. Each one a silent partner in a cosmic waltz. Saturn. Our ultimate destination for this journey will soon appear, a breathtaking vision of golden bands and shimmering rings, an impossible cosmic halo against the deepest blackness. It is a sight that stills the heart and expands the mind, filling it with a sense of humbling grandeur. And then, as if a small bright pearl emerging from the depths of a cosmic ocean, Rhea will drift into view. It is a world that has patiently orbited its giant parent for billions of years, a silent witness to the ebb and flow of cosmic time, to the slow, majestic unfolding of the universe. What stories does it hold within its icy shell? What whispers does its tenuous atmosphere carry like a faint echo from an ancient past? A breath in the void. These are the gentle questions we will ponder together, allowing our minds to wander freely, unburdened by the need for immediate answers, finding solace and beauty in the questions themselves, in the very act of reaching out to the unknown. The beauty of this journey lies not just in the discoveries themselves, but in the process of discovery, the quiet unfolding of knowledge like a delicate flower blooming in the cosmic garden. It is a reminder that the universe is an endless book, and we are forever its humble readers, always finding new pages to turn, new paragraphs to absorb, each one offering a deeper sense of connection to the vastness around us. Rhea, in its quiet existence, offers us a unique chapter, a chance to slow down and truly listen to the cosmic hum, to feel the gentle rhythm of distant worlds, a rhythm that has played out for eons. It teaches us patience, humility, and a boundless appreciation for the intricate wonders that lie just beyond our immediate reach, yet are always there for us to gently explore, to dream about, to let inspire our slumber, weaving themselves into the fabric of our subconscious. So let us begin this quiet journey, allowing the vastness of space to cradle our thoughts and the gentle mysteries of Rhea to fill our minds with peaceful contemplation. There is no rush, no pressure, only the serene unfolding of a cosmic story designed to soothe and inspire, to gently guide you towards a deeper sense of calm as you drift into sleep. We will delve into its very first moments of being known to humanity, tracing the quiet path of discovery that brought this icy world into our collective consciousness, a journey as old as human curiosity itself. A journey that started with a patient gaze and a quiet observation. Imagine Giovanni Domenico Cassini, the Italian astronomer, on that cold December night in 1672. The air would have been crisp, perhaps biting, but his focus would have been unwavering. His breath a quiet mist in the dark. His telescope, a marvel of its time, was his window to the heavens, a humble yet powerful instrument, allowing him to peer beyond the limits of human vision, to extend his senses into the cosmic beyond. He wasn't just looking. He was truly seeing, observing the intricate dance of light and shadow, searching for the subtle clues that the universe so generously yet discreetly offers. Like a shy friend, revealing secrets one by one, Cassini was a master of patience, understanding that the greatest revelations often come not from sudden dramatic flashes, but from consistent, methodical observation, from the quiet accumulation of data over countless nights. His work was a labor of love, a dedication to peeling back the layers of cosmic mystery. One meticulous observation at a time, like an archaeologist, carefully brushing away dust from an ancient artifact. He had already made significant contributions to our understanding of Saturn, unraveling some of its secrets. Like a skilled detective piecing together an ancient puzzle, mapping its various moons and the stunning divisions within its magnificent rings, a complex system that seemed to defy earthly logic. He had discovered other moons, tiny companions dancing around the ringed behemoth, each one a testament to the gravitational artistry of the solar system, a silent ballet choreographed by unseen forces. On that particular night, perhaps his eye caught a fleeting glimmer, a faint point of light almost lost in the overwhelming brilliance of Saturn itself. Or perhaps it was a persistent, barely perceptible shimmer that only the most dedicated gaze could discern, a whisper in the cosmic wind. It would have been a moment of quiet triumph, a silent connection between a human mind and a distant, unseen world, a meeting across billions of miles of empty space. The discovery of Rhea was not a loud celebratory fanfare, but a gentle whisper, a new name added to the celestial registry, a testament to the profound patience and keen intellect of Cassini. He had brought this silent moon, previously unknown to our conscious awareness, into the light of human understanding. Simply by the virtue of his persistent, unyielding gaze, a gaze that connected Earth to the distant reaches of Saturn's realm. This quiet act of discovery centuries ago laid the foundation for all that we know about Rhea today. It began with a simple observation, a gentle acknowledgement of a world existing far beyond our earthly concerns, yet now irrevocably linked to our story of exploration, to the ever-unfolding narrative of human curiosity. And it is this quiet beginning that invites us into Rhea's embrace tonight, allowing us to slowly unfold the layers of knowledge that have accumulated since that distant December night. We are in a sense continuing Cassini's patient vigil, extending his gaze further into the mysteries that Rhea still holds, letting our own minds wander where his once did, perhaps finding new questions, new pathways of thought as we drift deeper into the quietude of the night. This journey is not just about what we know, but about the profound beauty of what we don't know, and the quiet awe that such unknowns can inspire within us. Let us find peace in this vast, beautiful mystery. Now let us gently turn our gaze to the very beginning of Rhea's story, as far as our human records allow us to trace it. Imagine, if you will, the patient, unwavering focus of minds long past gazing up at the night sky, their tools simple, yet their curiosity profound. It was on a crisp December night, the 23rd of December in the year 1672, that a celestial whisper was first heard, a faint light glimpsed by an extraordinary Italian astronomer named Giovanni Domenico Cassini. He was a man of quiet dedication, whose life was a testament to the power of patient observation. Cassini spent countless hours at his telescope, meticulously mapping the heavens, not unlike a skilled cartographer, drawing the lines of an unseen land. His eyes, keen and persistent, sought out the subtle dances of the planets and their attendant moons, sketching their paths across the cosmic canvas with an artistry born of scientific rigor. Cassini was more than just a discoverer. He was a pioneer, a bridge between ancient astronomical observations and the dawn of modern science. Born in a small town in Italy, his early life unfolded amidst the quiet beauty of the countryside, but his gaze was always drawn upwards towards the boundless expanse above. He became a professor of astronomy at the University of Bologna. At a young age, a testament to his prodigious talent and insatiable thirst for knowledge. It was here that he began his monumental work, tirelessly observing the movements of planets, refining existing tables, and crucially making discoveries that would reshape our understanding of the solar system. His move to France at the invitation of King Louis XIV marked a new chapter where he became the director of the newly constructed Paris Observatory. Imagine this place, a hub of scientific endeavor, filled with the hum of intellectual pursuit. It was in these hallowed halls, with access to some of the most advanced instruments of his time, that Cassini truly soared. He was not merely looking through a lens. He was conversing with the cosmos, patiently coaxing its secrets into the light. He charted the intricate divisions within Saturn's rings, the delicate separation now famously known as the Cassini division, a testament to his acute observational skills. He also discovered 4 of Saturn's moons, Iapetus, Tethys, Dione, and, of course, Rhea. Each discovery was like finding a new silent note in a cosmic symphony, adding depth and complexity to the celestial music. The naming of this newly found moon Rhea also carries a gentle echo of ancient lore. It was named after the Titan goddess Rhea in Greek mythology, the mother of the Olympian gods and goddesses, including Zeus. This naming convention, linking celestial bodies to figures of myth, imbues them with a poetic resonance, bridging the grand narratives of human culture with the silent grandeur of the cosmos. Rhea, the mythological figure, represented motherhood, fertility, and the flow of time. It's a fitting name for a moon that has orbited for eons, a silent mother figure in Saturn's vast family of worlds, nurturing its own quiet mysteries. For centuries, astronomers and planetary scientists have looked upon this moon a subject of fascination, drawn by its very existence, by the simple fact that it is. Let us now gently settle into the basics of Rhea, its fundamental nature, its place in the grand cosmic ballet. Rhea is, as we now know, the second largest moon of Saturn, humbly following the mammoth Titan. Titan itself is a world of incredible intrigue, shrouded in a thick orange haze with lakes of liquid methane and a strange Earth-like cycle of precipitation. But Rhea, though smaller and seemingly less dramatic, possesses its own unique charm, a quiet beauty that invites a different kind of contemplation. To truly grasp Rhea's size, let's play a gentle game of cosmic comparison. With a diameter of 1,528 kilometers, it's roughly half the size of our own moon. Imagine gazing up at our familiar lunar companion, that beacon, in our night sky. Now imagine a world half its size, floating in the distant cold. It helps us to anchor this distant icy sphere in something we can relate to, something tangible. If we were to gently place Rhea next to Earth, just for a moment of quiet visualization, it would stretch from the bustling heart of London all the way to the historic streets of Warsaw. Such a comparison helps us to bridge the immense distances of space, bringing this faraway world a little closer to our understanding, allowing us to feel its gentle scale. Rhea's orbital dance around Saturn is a study in celestial rhythm. It orbits Saturn at a distance of about 527,000 kilometers, a path it traces with remarkable precision, a silent, graceful circle around its immense parent planet. To put this into perspective, our own moon orbits Earth at an average distance of about 384,400 kilometers. So Rhea dances a little further from its giant in a wider, more expansive embrace. The time it takes for Rhea to complete one full revolution around Saturn is also quite swift, at least by earthly standards. It completes one orbit every 4.5 Earth days. Imagine a week passing here on Earth, and Rhea would have completed almost 2 full journeys around its colossal companion. This relatively rapid orbital period means that Rhea is in constant gentle motion, a perpetual traveler in the Saturnian system, always maintaining its elegant dance. A common feature among large moons in our solar system, including Rhea, is that it's locked in a synchronous rotation with Saturn. This means that the same side always faces the planet, much like our own moon always shows us the same familiar face. Picture this: as Rhea glides through its orbit, it also rotates on its own axis, but its rotation period is exactly the same as its orbital period around Saturn. It's as if an invisible thread binds them, ensuring that one hemisphere of Rhea is perpetually gazing upon the majestic rings and swirling clouds of Saturn, while the other faces the endless, starry void. This synchronous lock is not a coincidence nor a random alignment. It's a profound consequence of the long-term gravitational embrace between a moon and its parent planet. Over billions of years, the gravitational pull of Saturn, uneven across Rhea's body, has exerted subtle tidal forces. These forces act like a gentle cosmic brake, gradually slowing down Rhea's rotation until it perfectly matched its orbital period. It's a beautiful testament to the unseen yet powerful forces that shape our universe. A slow, gentle negotiation between two celestial bodies until they find a perfect harmonious balance. This eternal facing has fascinating implications. One side of Rhea is always bathed in the reflected glow of Saturn, a world of constant daylight or Saturnlight, experiencing the ebb and flow of the giant planet's phases like our moon experiences phases of Earth. The other side, the far side, is a world of deeper darkness, illuminated only by the distant sun and the scattering of starlight, a silent, solitary vigil against the vastness. Could this constant orientation have subtly influenced the evolution of its two hemispheres? Might one side have experienced different temperature regimes, different patterns of impact, or even different geological processes over eons? These are the kinds of gentle questions that arise when we contemplate such a precise, synchronous dance, inviting us to imagine the subtle differences painted across its silent surface. The very concept of a moon locked in this perpetual embrace evokes a sense of timelessness, of a cosmic devotion. Rhea, forever tethered by gravity's invisible reins, performs its silent, unchanging ballet. It's a reminder that even in the chaotic dance of the cosmos, there are islands of serene order, predictable rhythms that resonate with a quiet beauty. This steady synchronous spin and orbit also provide invaluable data for scientists. By observing its precise movements, they can infer details about its mass distribution, its internal structure, and the subtle gravitational tugs it experiences from Saturn and its other moons. Each tiny wobble, each minute deviation from a perfect path becomes a whisper of information, a clue in the grand cosmic detective story. So, as we imagine, Rhea let us not just see a distant sphere of ice, let us see a world with a rich if silent history, a place meticulously observed by pioneers like Cassini, a celestial body intimately connected to the grand dance of its parent planet. Its size, its orbit, and its synchronous rotation are not just cold facts, but rather threads in a cosmic tapestry, each one contributing to the unique character of this gentle moon. It's a world that has patiently awaited our deeper gaze, a world that invites us to slow down to observe and to wonder at the intricate, elegant machinery of the solar system. A mechanical ballet performed with breathtaking grace, all for the silent admiration of those who choose to look. The journey we are on is one of gentle unfolding, allowing each piece of information about Rhea to settle into our minds, not as a burden, but as a soft, comforting presence. We are building a mental image of this moon layer by layer, starting with its fundamental identity, a discoverer's triumph, a mythological namesake, and a cosmic dancer, locked in an eternal embrace. This foundational understanding allows us to appreciate the deeper mysteries that we will soon explore, the intricacies of its surface, its tenuous atmosphere, and the hidden depths of its interior. Each step is a quiet exploration, a deepening of our connection to this distant, silent world, bringing it closer to our dreams. Let us now gently shift our attention from Rhea's silent dance through space to the very canvas of its being, its surface. Imagine a world sculpted primarily from ice, not the dark, murky ice we might find on Earth, but a pristine, almost dazzling expanse. One of the most striking characteristics of Rhea is its extraordinary reflectivity. It possesses an albedo of 0.7, which in simpler terms means it reflects a remarkable 70% of the sunlight that touches its surface. Picture a mirror perfectly polished, catching and throwing back the light. Rhea in the vast, dark theater of space appears as a brilliant, almost blinding white against the backdrop of scattered stars and the deep cosmic void, like a cosmic pearl gleaming in the perpetual twilight. This high reflectivity is a hallmark of its composition, a visual signature of its icy nature, a beacon visible from far across the Saturnian system. Why does it shine so brightly? Its surface is primarily made of water ice. This isn't just a thin frost, a delicate dusting that might melt away with the dawn. It's the very bedrock of the moon, miles deep in places. Imagine oceans frozen solid, not for days or years, but for billions of years, creating a vast glittering expanse that has withstood the relentless cold of space for eons. This purity of its icy facade is what allows it to capture and bounce back so much of the faint sunlight that reaches it, making it a luminous pearl in the distant Saturnian system. It's a silent, constant beacon, a testament to the abundance of water in its frozen form. In the outer reaches of our solar system, a stark and beautiful contrast to the fiery sun that provides its distant illumination. However, despite this seemingly pristine reflective quality, Rhea is far from a featureless ice sheet. If you were to gently drift closer, allowing your gaze to soften and sharpen, you would begin to discern a rich, intricate tapestry woven across its surface. This moon is heavily cratered, telling a silent yet powerful story of ancient impacts and a long, tumultuous history. Each crater is a scar, yes, but also a window, a moment frozen in time, capturing the echoes of a violent cosmic past like permanent ripples in a frozen pond. They are like pockmarks on an ancient face, each one a testament to countless encounters with cosmic debris meteors and comets that have hurtled through the solar system over eons, leaving their indelible marks. These aren't mere imperfections. They are chronicles etched in ice, narrating a grand, brutal ballet of collisions that shaped not just Rhea, but countless worlds throughout our cosmic neighborhood. Imagine a gentle snowfall, but instead of delicate flakes, imagine boulders of rock and ice, some as small as pebbles, others as large as mountains raining down from the heavens over geological timescales. Each one leaves an impression, a circular wound on the moon's frozen skin. The sheer number of these craters on Rhea suggests an incredibly old surface one that hasn't been significantly resurfaced or smoothed over by geological activity in a very, very long time. It's a bit like an ancient forest floor where every fallen leaf and branch from millennia past lies undisturbed, forming a deep, undisturbed layer, a historical record preserved beneath layers of time. In this way, Rhea's surface acts as a cosmic archive, preserving the record of intense bombardment that was far more common in the early days of our solar system, when leftover debris from planet formation was still abundant and crisscrossing the orbits of the nascent worlds like leftover dust in a cosmic workshop. The largest of these ancient wounds is a truly magnificent spectacle, a vast depression known as Mamaldi. This colossal crater spans an impressive 480 kilometers in diameter. To give you a sense of its immense scale, picture the distance from the romantic boulevards of Paris to the charming canals of Amsterdam. That's how wide Mamaldi stretches across Rhea's icy face. Imagine standing at one edge of this colossal basin and trying to glimpse the other side. It would disappear over the horizon, a curved expanse so vast it defies easy comprehension, a curvature dictated by the moon's own spherical shape. Mamaldi is not just a crater. It's a silent monument to an impact of unimaginable force, an event that must have sent shockwaves rippling through Rhea's very core, altering its landscape on a truly planetary scale. It whispers of a time when the solar system was a far more dangerous place, a cosmic shooting gallery where worlds were forged and scarred in spectacular fashion, each impact a stroke in the creation of the celestial bodies we see today. These craters, however, are not just passive scars on Rhea's surface. They are active, silent storytellers, providing us with invaluable windows into the moon's past and composition. Scientists, with their keen eyes and sophisticated instruments, have observed something particularly intriguing about these ancient bowls. The bottoms of some craters appear darker than the surrounding terrain. Imagine looking at a pristine white canvas and then seeing faint, smudged shadows at the very base of some depressions, a subtle variation in the uniform brightness. This subtle variation in color is a profound clue, a whispered hint about what lies beneath the surface, like seeing a darker stone at the bottom of a clear, shallow stream. This darker appearance could indicate that the sheer force of these ancient impacts excavated material from beneath Rhea's bright surface. Think of digging a hole in a snowfield that seems uniformly white on top, only to uncover darker earth or rock just beneath the surface. Similarly, these impacts might have dug deep enough to expose darker amorphous water ice and impact melt. Amorphous ice is water ice that lacks a crystalline structure, often formed under specific conditions of extreme cold and pressure or rapid freezing, making it appear less reflective than its crystalline counterpart. It's like the difference between a perfectly formed snowflake and a chunk of frozen slush. Impact melt, as its name suggests, is material that was melted by the incredible energy released during the collision and then resolidified, often incorporating darker materials from deeper within the moon or from the impacting body itself, creating a darker, more mottled texture. In the quiet observation of photographs, such as those captured by our robotic envoys like Cassini, you can indeed see this phenomenon. Imagine a specific crater in the southern hemisphere of Rhea. Its outer edges still bright with ejected material, blasted out from the impact and settling back down like a frosty blanket, radiating outward from the point of collision. Yet at its heart, a darker hue, a subtle stain hinting at the deeper secrets that the impact brought to light. It's a visual metaphor for discovery sometimes. To truly understand something, you must break its surface, even if the act of breaking leaves a mark. These darker patches are not flaws, but revelations offering silent testament to the churning forces of the early solar system when Rhea was taking shape under a barrage of cosmic blows, like a sculptor chipping away at raw stone to reveal the form within. They tell a story of layers of a complex history hidden just beneath that dazzling reflective exterior, waiting for us to interpret their silent language to understand the ancient whispers embedded in their very composition. The profound beauty of these observations lies in their ability to transport us through time. Each crater, each variation in surface hue, is a gentle echo from billions of years ago. It allows us to imagine the colossal forces at play, the unimaginable energy released when a celestial body, perhaps an asteroid or a comet, slammed into nascent Rhea. The impact would have been an event of cataclysmic proportions, sending shock waves rippling across the moon's entire being, deep into its icy crust, perhaps even altering its internal structure in ways we are only just beginning to comprehend. The ejected material would have flown out into space, some escaping into the vast void, while much of it would eventually fall back down, creating secondary craters or forming the bright ejecta blankets we observe around some of the larger impacts, like snow settling after a massive blizzard. This process of bombardment, while violent, was also a crucial part of planetary formation and evolution. It delivered new materials, rearranged existing ones, and carved out the landscapes we see today, shaping worlds one impact at a time. Rhea, in its heavily cratered state, is a pristine record of this early chaotic era. It's like a cosmic diary, its pages filled with the indelible ink of celestial collisions, each one a silent chapter in the grand narrative of our solar system's birth and youth, a story written in stone and ice. It's a testament to the persistent, transformative power of collisions, not just as destructive forces, but as architects of the cosmic landscape. And as we contemplate these ancient scars, these silent witnesses to bygone eras, we are reminded of the resilience of these worlds. Despite the incredible forces unleashed upon them, they endure, continuing their silent orbits, carrying their history etched upon their faces for all of cosmic time. Rhea's bright reflective surface punctuated by these dark-bottomed craters is a testament to both the destructive power of the cosmos and the enduring nature of its creations. It's a delicate balance of light and shadow creation and destruction, all harmoniously integrated into the silent, beautiful dance of a distant moon. We are but humble observers, grateful for the opportunity to glimpse these profound stories, to let their quiet resonance fill our minds as we drift towards sleep, knowing that even in the vastness, there is an intricate beauty in every detail. This frozen canvas of Rhea speaks volumes without uttering a single sound, a silent narrator of cosmic history. As we continue our gentle journey across Rhea's silent icy expanse, let us now turn our gaze to some of its most intriguing features, those subtle markings that tell tales of inner stirrings and ancient upheavals. Beyond the vast circular imprints of impact craters, there exists a delicate tracery, a system of bright, wispy streaks that crisscross its surface. Imagine, if you will, the finest lines drawn by an unseen artist across a canvas of brilliant white, intricate patterns that seem almost too delicate to be part of such a rugged, cratered world. These wisps are not random scribbles. They are profound geological signatures, silent witnesses to forces that once stirred within Rhea's frozen heart, much like faint, lingering memories of a dream. These enigmatic streaks were first observed in detail by the Voyager space probes in the early 1980s. When Voyager 1 and Voyager 2, those intrepid robotic pioneers, made their fleeting visits to the outer solar system, they sent back grainy yet revolutionary images of Saturn and its many moons. Even with the technology of that era, which seems rudimentary by today's standards, these faint, bright lines on Rhea's surface caught the eyes of keen scientists. They were puzzling, appearing almost ethereal, like traces of frost left by a passing cosmic breath or thin scratches on an ancient lens. Their true nature, however, remained shrouded in mystery, an open question whispered among researchers awaiting a more precise and revealing gaze. The images were compelling, intriguing enough to spark deep curiosity, but not quite sharp enough to fully unravel the secret of these delicate patterns. They were like a half-heard melody, hinting at a grander composition, yet leaving much to the imagination, a tantalizing enigma suspended in the cold vacuum. Decades later, the Cassini mission arrived, a marvel of modern engineering and scientific dedication, poised to spend years in the Saturnian system, meticulously peeling back its layers of mystery. Cassini was a spacecraft designed for patience and precision, a robotic explorer, capable of returning to the same points again and again, to gather more data, to refine its vision. With its much more advanced instruments and the capability for high-resolution imaging, Cassini provided the clarity that Voyager could only hint at. It was as if a hazy photograph suddenly came into sharp focus, revealing breathtaking details previously unseen. And what it revealed about these wisps was truly astonishing, transforming a subtle curiosity into a profound geological revelation. They were not mere deposits of frost or shallow veins of ice that might form from surface sublimation. No, these wisps were ice cliffs, some rising hundreds of meters high, silent, towering walls of frozen water reaching towards the distant sun, catching its light with an almost defiant brilliance. Imagine yourself not an astronaut, but a tiny mote of dust, gently floating above Rhea, slowly descending towards its surface. As you draw closer, the faint lines you saw from afar begin to resolve into massive geological features. You might see a sheer vertical face of ancient ice, reflecting the faint sunlight with blinding intensity, a wall of pure crystalline frozen water. These aren't jagged, chaotic breaks like splintered wood. Instead, they often appear as long linear escarpments stretching for considerable distances across Rhea's curved surface, sometimes for hundreds of kilometers. Picture long parallel lines carved into the icy landscape, sometimes intersecting at sharp angles, sometimes curving gently with the moon's contours, creating a vast, intricate network that seems both deliberate and natural. They are reminiscent of the canyons and fault lines we see on rocky planets like Mars or even Earth. But here in this distant frigid realm, they are sculpted from pure pristine ice, a material that on Earth is so fleeting and dynamic. These icy ramparts are a stark and beautiful contrast to the otherwise gently undulating terrain of craters, standing as proud declarations of Rhea's deep geological past, a testament to forces that molded its very skin. The very existence of such dramatic cliffs, especially on a moon, thought to be relatively inactive, immediately raised profound questions about their origin. For a long time, Rhea was considered a dead world, its surface shaped primarily by external impacts rather than internal stirrings. But these cliffs painted a different picture, suggesting a more dynamic history. Scientists began to piece together a story not of external forces like meteor strikes, but of internal stirrings of forces emanating from within Rhea's frozen heart. Think of our own Earth, where immense tectonic plates slowly grind against each other, building mountains and tearing open valleys, a process driven by the planet's internal heat. While Rhea's internal dynamics are far less energetic than Earth's, and its plates might be more like vast sheets of ice than rocky continents, the principle is similar. In Rhea's geological history, its icy crust must have experienced periods of immense stress and strain. Imagine the moon's frozen skin, a shell of ice perhaps tens or even 100 kilometers thick, subjected to the slow, relentless push and pull of internal forces. These forces could be due to the gradual cooling and contraction of its interior, causing the outer shell to shrink and crack. Or they might be subtly influenced by tidal stresses from Saturn's immense gravity. As Rhea orbits Saturn, the giant planet's gravitational pull exerts a varying squeeze and stretch on the moon, especially if Rhea's orbit was slightly more elliptical in the past. This constant flexing, though imperceptible on human timescales, can build up stress within the brittle icy crust. Over vast timescales, this stress accumulated until the icy crust could no longer bear the tension. It fractured much like a sheet of ice, cracking on a frozen lake under the weight of a sudden shift or a pane of glass giving way under pressure. And in some sections, due to this fracturing, the icy crust was thrust upward, creating these remarkable elevated features, these towering walls of ice. It's a slow, quiet process of uplift, a testament to the moon's internal dynamics over billions of years, a silent, monumental struggle against the forces of compression and tension. Other sections might have dropped down, creating corresponding valleys or grabens, making the cliffs the elevated edges of these ancient rifts, the visible remnants of a colossal slow motion tearing apart of the moon's surface. These features, these bright linear cliffs, are more than just visually striking. They are precious clues about the moon's geological history and the processes that have shaped its surface over billions of years. They tell us that Rhea, despite its appearance as a static, heavily cratered world, has not always been entirely dormant. It has experienced periods of internal activity, periods when its icy shell stretched, buckled, and broke, revealing the subtle power of its hidden forces. Understanding the orientation, length, and height of these cliffs helps scientists reconstruct the stress patterns within Rhea's crust, painting a detailed picture of its ancient geological epochs. Were these periods of activity linked to changes in its orbit around Saturn, leading to stronger tidal heating or flexing? Or perhaps to internal processes like differentiation, where heavier materials sink to the center and lighter ones rise, or even the slow, inexorable freezing of a subsurface ocean, if one ever existed beneath its crust. Each cliff is a silent paragraph in a very old book waiting for careful interpretation, a piece of a grand cosmic puzzle that requires patient study. The existence of these bright streaks also connects profoundly to Rhea's high reflectivity, its dazzling albedo. These freshly exposed ice surfaces, often steeper and perhaps less contaminated by the constant rain of micrometeorite dust over time due to their vertical nature, might contribute significantly to Rhea's overall dazzling appearance. They are like freshly polished facets on a cosmic diamond, catching and reflecting sunlight with exceptional efficiency, standing out against the slightly more weathered and dust-covered surrounding terrain. This suggests a dynamic interplay between internal geology and surface appearance, where the very forces that shaped the cliffs also contribute to the moon's brilliant demeanor, a feedback loop of cosmic beauty and geological transformation. The constant exposure of new ice by slow faulting and fracturing could help maintain the moon's bright appearance over eons, preventing it from darkening as much as some other older surfaces in the outer solar system. Consider the immense timescale involved in the formation and preservation of these features. These are not ephemeral formations like ice flows on an earthly sea. They were likely formed in the moon's distant past, perhaps in its youth, when its interior was warmer and more dynamic, or when its orbital eccentricity around Saturn was different, leading to stronger tidal flexing. Over billions of years, these cliffs have remained a testament to the stability of Rhea's geology since those ancient events, standing as silent monuments preserving their form against the relentless barrage of micrometeorites that slowly darken and erode most exposed surfaces in the solar system. Their continued brightness, despite their profound age, is another puzzle perhaps, hinting at their pure composition or the way they interact with the space environment, shedding dust or remaining exceptionally clean due to some subtle process. The contemplation of these ice cliffs invites us to imagine a world far more complex than a simple frozen sphere. It suggests a history of slow, deliberate changes of internal pressures building and releasing over eons, shaping the very face of the moon, much like a potter slowly shaping clay on a wheel. It's a reminder that even in the quietest corners of our solar system, in realms of unimaginable cold and vast distance, there are profound stories of geological evolution waiting to be discovered, inscribed not in rock and fire, but in ice and silence, a testament to the diverse ways worlds are born and mature. Each bright streak, each towering cliff is a gentle invitation to deeper thought, to a broader understanding of the subtle yet powerful forces that govern celestial bodies, forces that operate on timescales beyond human comprehension, yet leave their indelible marks for us to ponder. These are not the dramatic volcanic plumes of Enceladus spewing geysers of water ice into space, nor the vast rust-colored canyons of Mars carved by ancient rivers. Rhea's ice cliffs represent a quieter, more subtle form of planetary sculpture. They speak of a different kind of geological activity, one shaped by the unique properties of ice under immense pressure and cold, and by the relentless gravitational embrace of a giant planet. Rhea's ice cliffs are its quiet declaration of a geological past, a testament to its dynamic nature despite its current serene appearance. They encourage us to look beyond the obvious, to seek the hidden narratives within the landscapes of distant worlds, to appreciate the unique ways in which each celestial body tells its own story through its very form, a silent language understood by the patient observer. As we drift toward sleep, let these bright, silent cliffs stand tall in your mind, illuminated by the distant sun, guarding the ancient secrets of Rhea. They are a testament to the moon's enduring beauty and the mysteries that still lie beneath its reflective surface. They remind us that even the most desolate-seeming places in the universe can hold profound and beautiful stories, waiting for us to listen with an open mind and a quiet heart. As we continue our serene journey across Rhea's ancient ice-carved surface, let us now delve into one of its most surprising and intriguing revelations, a discovery that truly expanded our understanding of what a moon in the outer solar system could possess. Imagine, if you will, the vast, cold emptiness of space, seemingly devoid of anything but faint starlight and distant worlds, a silent, infinite canvas. It is within this seemingly perfect vacuum that a subtle breath and ethereal whisper was detected around Rhea. In 2010, data from the Cassini spacecraft led to a surprising announcement. Rhea appeared to have a tenuous atmosphere or exosphere. This was a moment that shifted our quiet understanding of these distant icy realms. Now, the very idea of an atmosphere, however thin, around an icy moon like Rhea is quite remarkable. We often associate atmospheres with larger, more geologically active bodies like our own vibrant Earth, or with those massive gas giants themselves, shrouded in thick blankets of swirling gases. A small amount of gas, a scattering of atoms gently nudged from a surface by solar winds or micrometeorite impacts, is perhaps expected around any celestial body, a constant, imperceptible shedding. But for Rhea, what was truly unexpected was that there was enough of this gas to be measurable to register distinctly and consistently on Cassini's exquisitely sensitive instruments. It wasn't a dense blanket like Earth's, or even the hazy hydrocarbon-rich shroud of Titan. It was more like a gossamer veil, a mere wisp of gas, a fragile breath in the cosmic void. Yet its very presence, however thin, was a profound scientific marvel, a silent declaration that even the seemingly most inert worlds hold hidden complexities. The detected atmosphere consisted primarily of oxygen and carbon dioxide. Imagine for a moment trying to breathe on Rhea. Even if you could miraculously survive the unimaginably frigid temperatures and the near-absolute vacuum, this breath would be incredibly thin. The oxygen detected was about 5 trillion times less dense than Earth's atmosphere at sea level. To truly grasp this astounding difference, picture the air around you right now dense enough to carry sound, to rustle leaves, to fill your lungs with a life-giving embrace. Now imagine thinning it out, removing molecule after molecule thinner and thinner until it's almost beyond imagination. It would be akin to having only a handful of air molecules scattered throughout a vast cathedral, or trying to hear a whisper from across an entire continent. Yet while incredibly thin, almost imperceptible by our earthly standards, this mere presence of a measurable, though extremely tenuous atmosphere, raised intriguing questions about its origin and its ability to sustain itself in such a harsh environment. Where did this breath in the void come from? And how does it persist, even in such a delicate form, against the relentless forces of solar radiation and the vacuum of space that constantly try to strip away every atom? One prevailing theory suggests a fascinating and rather elegant origin for this ethereal oxygen. It proposes that the oxygen is produced by the decomposition of water ice on Rhea's surface when it's struck by energetic ions from Saturn's magnetosphere. Imagine Rhea's vast reflective icy surface, a silent canvas stretched across billions of years. This surface is not just bathed in faint sunlight. It is constantly bombarded by a silent, invisible rain of energetic charged particles or ions streaming from Saturn's powerful magnetic field. Saturn's magnetosphere is an immense dynamic region of space, dominated by the planet's magnetic field, acting like a colossal invisible shield that traps and accelerates these charged particles, creating a bustling, turbulent, yet unseen environment around the giant planet. When these high-energy ions collide with the water ice on Rhea's surface, they act like tiny, relentless cosmic hammers, striking the ice with enough force to break apart the strong chemical bonds of the water molecules. Water, as you know, is made of hydrogen and oxygen, H2O. When the ions strike, they can literally split the water molecules apart, freeing the oxygen atoms from their hydrogen companions. These newly liberated oxygen atoms, now individual gas particles, are no longer bound to the solid ice. They can then float up from the surface, gently drifting into the space around Rhea, slowly accumulating to form this incredibly tenuous exosphere, a mere ghost of an atmosphere. It's a subtle, ongoing process, a silent act of cosmic chemistry happening continuously on Rhea's cold, exposed surface, a quiet yet persistent contribution to its ethereal envelope. The carbon dioxide, on the other hand, is thought to have a slightly different yet equally intriguing origin, a testament to the complex chemistry that can unfold even in such extreme environments. It is believed to be the result of organic molecules on the surface being oxidized by the oxygen in the exosphere. Picture tiny specks of carbon-containing organic molecules. These could be primordial remnants from ancient cometary impacts that delivered carbon-rich material to Rhea in the early solar system, or perhaps they have been brought up from deeper within Rhea's interior by subtle geological processes. These organic molecules rest upon or are embedded within the surface ice. As the newly liberated oxygen atoms sparse as they are drift in the whisper-thin exosphere above Rhea, they can chemically react with these organic molecules. This reaction, a slow process of oxidation, a cosmic rusting if you will, would produce carbon dioxide gas, which then joins the oxygen in Rhea's tenuous atmosphere, adding another component to its ghostly breath. It's a subtle dance of chemical transformation, suggesting that even on this cold, distant world, complex molecular interactions are taking place, hinting at a fascinating and unexpected chemical environment. A quiet laboratory in the vastness of space. This discovery was not just surprising, it was profoundly significant for our understanding of planetary science. It made Rhea the first moon known to have an oxygen atmosphere other than Jupiter's moons, Ganymede and Europa. Ganymede, the largest moon in the solar system, and Europa, a world famously thought to harbor a vast subsurface ocean beneath its icy crust, both have incredibly thin oxygen atmospheres produced by similar interactions of charged particles with their icy surfaces. For Rhea, a smaller, seemingly less geologically active world than these Jovian giants, to share this characteristic was a testament to the pervasive nature of these atmospheric formation processes throughout the outer solar system. It suggests that such ethereal breaths might be far more common than we once thought, hinting at a new layer of complexity for seemingly simple icy worlds, turning what we once considered barren into subtly active chemical landscapes. It broadened our definition of atmosphere itself, pushing beyond the dense envelopes of gas giants or rocky planets to include these faint, shimmering halos. Furthermore, this revelation opened up vast new avenues for research into the complex and often invisible interactions between Saturn's moons and the planet's powerful magnetosphere. Each moon in Saturn's system, from the innermost Mimas, battered and heavily cratered, to the distant haze-shrouded Titan, is constantly bathed in the flow of charged particles emanating from Saturn's immense magnetosphere. This discovery on Rhea provided a unique case study, a real-world example allowing scientists to refine their theoretical models of how these magnetospheric interactions can sculpt and influence the surfaces and tenuous envelopes of icy worlds. It encouraged a deeper, more nuanced look into the subtle energy exchanges, the invisible currents of particles and fields that shape the environments of these distant satellites, far from the direct heat of the sun. It's a reminder that the space around planets is not truly empty, but a dynamic, swirling environment filled with unseen forces and particles, constantly interacting with anything that passes through it. The magnetosphere is not just a shield. It's also an active participant in shaping the very nature of these moons, a cosmic sculptor working with invisible tools. The implications of Rhea's exosphere extend beyond just its immediate composition. The presence of carbon dioxide in particular raises fascinating questions about the long-term chemical evolution of this moon. Are these organic molecules primordial, dating back to the very formation of the solar system, preserved in the deep freeze of Rhea's ice, like tiny time capsules? Or are they being generated through some ongoing process, a continuous, slow creation in this frigid environment? The interplay between oxygen and organic compounds in such an extreme low-pressure environment might even offer clues to the early chemistry of life, suggesting conditions under which complex molecules might form or break down in the absence of liquid water, providing insights into the very earliest steps towards chemical complexity in the universe. While Rhea's atmosphere is undoubtedly too thin and its environment too harsh to support life as we know it, Its peculiar chemical processes provide a fascinating natural laboratory for understanding astrochemistry in cold, icy environments, expanding our understanding of where life's fundamental building blocks might arise. Moreover, this discovery profoundly refined our understanding of how atmospheres are formed in the outer solar system. It underscored that volcanic activity, or the simple sublimation of surface ices where ice turns directly into gas, are not the only ways for celestial bodies to acquire a gaseous envelope. Charged particle bombardment, a process often overlooked or underestimated in traditional atmospheric studies, emerges as a significant contributor, especially for airless or near-airless icy bodies that lack internal heat to drive other atmospheric processes. This broadened perspective allows scientists to look for similar phenomena on other moons and distant icy dwarf planets, constantly refining our senses of atmospheric worlds in our cosmic neighborhood, making the universe seem even richer and more subtly alive than we previously imagined. Imagine the quiet revolution this discovery sparked among planetary scientists, a subtle shifting of paradigms. For so long, the focus was often on moons with thick Earth-like atmospheres, or conversely, on those considered utterly airless. Rhea revealed a subtle yet profound middle ground, a ghost of an atmosphere, a fragile whisper of gas in the cosmic void. It's a testament to the power of sensitive instruments and dedicated observation, which allow us to perceive the most minute details of distant worlds, unlocking secrets that were once unimaginable, extending our senses across vast distances. This exosphere, thin as it may be, is a constant gentle reminder that even the seemingly desolate can hold astonishing complexities, waiting for our patient gaze to bring them into focus, transforming what we once perceived as static into something subtly dynamic. It adds another layer of wonder to Rhea, transforming it from a mere ball of ice into a subtly breathing world with its own peculiar breath, contributing to the silent symphony of the Saturnian system in its own unique, understated way. As you drift deeper into the quietude of sleep, let the image of this whisper-thin atmosphere, silently exhaling oxygen and carbon dioxide into the vastness, fill your thoughts with a sense of gentle awe for the hidden intricacies of the cosmos. Having gently explored Rhea's shimmering surface and its whisper-thin atmosphere, let us now embark on an even deeper journey, a descent into the very heart of this icy moon. While we cannot directly observe what lies beneath Rhea's frigid bright surface, much like we cannot truly see the core of our own Earth, without sophisticated tools, scientists have used various ingenious methods to infer its internal structure. It's like listening for echoes in a vast silent cave, interpreting the subtle reverberations to understand the hidden architecture within. These methods rely on careful measurements from passing spacecraft, providing silent clues about the moon's hidden composition and arrangement. One of the primary clues comes from Rhea's average density. Imagine taking the entire moon, compacting it into a perfectly uniform ball, and then measuring its weight relative to its size. Based on Rhea's average density of 1.236 grams per cubic centimeter, which is only slightly higher than that of water, we can deduce its fundamental makeup. Pure water in its liquid form has a density of approximately 1.0 gram per cubic centimeter. Ice, being less dense, floats. The fact that Rhea's average density is just a little more than that of water leads to a profound conclusion. Rhea is composed primarily of water ice, about 75%, and a smaller fraction of rocks, the remaining 25%. This composition tells us a great deal. Imagine a colossal snowball, not packed with pristine white powder, but with a generous mixture of terrestrial rock, like tiny grains of sand or pebbles, mixed into the frozen water. Because of this structure, Rhea has often been described as a frozen, dirty snowball. It's a simple, yet evocative metaphor that immediately paints a picture of a world quite different from our own. This puts Rhea in stark contrast to moons like our own moon, which are primarily rocky bodies, dense and solid through and through. Our moon, forged in a fiery impact, is mostly silicate rock and metal, a testament to a very different birth and evolutionary path. Rhea, on the other hand, belongs to a family of icy worlds where water in its frozen state is the dominant building material, a cosmic testament to the sheer abundance of H2O in the outer solar system. This understanding of its density allows us to peer beyond its bright surface and envision the icy depths beneath a world built almost entirely from the very substance that sustains life here on Earth, albeit in a perpetually frozen state. When the Cassini spacecraft journeyed through the Saturnian system, its instruments weren't just taking pictures. They were meticulously analyzing the light reflected from Rhea's surface, a technique known as spectroscopic observations. These observations provided invaluable data about Rhea's composition, confirming what the density measurements suggested: water ice is indeed the dominant component of Rhea's surface. It's like a cosmic fingerprint analysis confirming the presence of a signature compound. But Cassini, with its unprecedented sensitivity, also detected the presence of other materials, subtle hints of more complex chemistry embedded within the ice. One surprising discovery was the detection of carbon dioxide trapped in the surface ice. Imagine the ice on Rhea not as a monolithic pure block, but as a vast porous structure within which tiny pockets of other gases and compounds have been held captive for eons. This finding suggests that Rhea's ice isn't pure water. It contains other compounds, possibly including complex organic molecules. Now, the term organic in this scientific context doesn't necessarily mean living or biological. It simply refers to molecules that contain carbon, often bonded with hydrogen, oxygen, and nitrogen. These are the fundamental building blocks of life as we know it, but they can exist in purely geological or chemical forms long before any biology arises. The presence of these trapped organic molecules is a profound whisper from Rhea's past. How did they get there? Were they incorporated during the moon's formation remnants of the primordial cloud of gas and dust from which the solar system condensed? Or were they delivered later by comets or meteorites, cosmic messengers carrying the ingredients for life across vast distances? This discovery suggests that Rhea's interior, and certainly its outer layers, are not just frozen water, but a complex chemical mixture, a cosmic repository of ingredients that could, under different circumstances, perhaps one day foster life. It adds another layer of intrigue to the frozen, dirty snowball image, suggesting a richer, more chemically active interior than previously imagined. Moving deeper into the inferred structure, we encounter a prevailing scientific model concerning Rhea's internal layering, or lack thereof. Due to its relatively low density, and importantly its higher moment of inertia, most scientists believe that Rhea is not differentiated into layers. To understand the moment of inertia, imagine spinning a figure skater. When their arms are outstretched, they spin slower. When they pull their arms in close, they spin faster. This is because the distribution of their mass changes their moment of inertia. For a celestial body, a lower moment of inertia means its mass is concentrated more towards its center, like a differentiated planet with a dense core allowing it to spin more easily. A higher moment of inertia means its mass is distributed more evenly throughout from core to surface. Rhea's relatively high moment of inertia suggests that its heavy rocky materials are not significantly concentrated in a distinct core with lighter ice floating above it, as would be the case in a fully differentiated body. Instead, it is thought to be a homogeneous mix throughout, with the exception of its core. Imagine a colossal frozen parfait, but instead of distinct layers of fruit and cream, the ingredients are largely blended together from top to bottom. The rocky material and water ice are mixed almost uniformly throughout its interior, forming a slushy, icy, rocky matrix rather than distinct concentric shells. This implies that Rhea might never have fully heated up enough during its formation to allow its heavier rocky components to sink to the center and its lighter ice to rise to the surface, a process called differentiation, which occurs on larger, more energetic worlds. The only exception to this homogeneous mix might be a very small, somewhat denser rocky core, a slight concentration of the heavier elements at its very heart, but not a distinct, well-defined core like Earth's. However, the beauty of science lies in its constant questioning and evolution, and not all scientists agree on a perfectly homogeneous interior. In 2006, a paper was released in the journal Icarus that suggested Rhea might have a layer of liquid water under its surface, a subsurface ocean. Imagine a secret sea, vast and dark, hidden beneath miles of solid ice, warmed by subtle forces, perhaps radioactive decay within its small rocky core, or the gentle constant kneading of tidal forces from Saturn. While this idea is still highly speculative and not as well supported as the subsurface oceans on moons like Europa or Enceladus, it's an intriguing possibility that continues to spark scientific curiosity. Europa, for instance, shows clear signs of active geological processes linked to its ocean-like chaotic terrain and potential plumes. Enceladus actively spews geysers of water ice into space from its south pole, direct evidence of a liquid reservoir. Rhea doesn't exhibit such dramatic direct evidence, making its potential ocean a more subtle, whispered hypothesis. Yet the presence of such an ocean, even a hypothetical one, would have significant implications for Rhea's potential habitability. Wherever liquid water persists for long periods combined with a source of energy and the right chemical ingredients, the possibility for simple forms of life, however, rudimentary, cannot be entirely dismissed. It would transform Rhea from a mere frozen, dirty snowball into a potential candidate for astrobiological interest, however remote. Furthermore, the existence of such an ocean would expand our understanding of the conditions necessary for liquid water in the outer solar system. It would suggest that internal heating mechanisms, even subtle ones, can be effective far from the sun, and that our current models for icy moon interiors might need to be re-evaluated to account for such hidden reservoirs. It's a testament to the persistent mystery of the universe, always ready to surprise us with hidden depths, even in the most seemingly desolate of places. Rhea's interior therefore contains mysteries that continue to puzzle and fascinate scientists, much like an ancient unopened box. But one of the most puzzling features related to Rhea's internal state is its shape. While many large moons and planets tend towards a perfect sphere due to their own gravity pulling all their mass equally towards the center, Rhea is noticeably non-spherical. It's not perfectly round, but rather slightly flattened at the poles and bulges at the equator, a shape we call a triaxial ellipsoid. Imagine taking a perfectly round ball and gently squeezing it at the top and bottom, and then slightly elongating it along one axis around its middle. This subtle distortion is a common outcome of rotation, where the centrifugal force at the equator causes a bulge. What's strange is that Rhea's shape doesn't quite match what we'd expect based on its rotation rate. Given how slowly it rotates due to its synchronous lock with Saturn, its bulge should be more modest, more symmetrical. This discrepancy has led scientists to propose that Rhea might have a non-uniform internal structure where denser material is concentrated away from its center in subtle ways. Perhaps the distribution of rock and ice isn't as perfectly homogeneous as initially thought, or there are subtle variations in density caused by ancient impacts or slow internal shifts that we cannot yet fully decipher. It's a subtle imbalance, a cosmic secret kept within its icy heart, hinting at complexities that current models struggle to fully explain. This odd shape is like a faint ripple on the surface of a pond, hinting at something stirring beneath a gentle invitation to further study and contemplation, pushing the boundaries of our understanding of how celestial bodies are truly formed and how they evolve over eons. It serves as a beautiful reminder that the universe, even in its quietest corners, holds profound mysteries that continue to inspire our wonder and deepen our humble inquiry. We have journeyed deeply into the inferred structure of Rhea, sensing the icy mix of its interior and pondering the subtle mystery of its non-spherical form. Now let us dwell a little longer on perhaps the most tantalizing whisper from Rhea's hidden depths, the intriguing possibility of a subsurface liquid water ocean. Imagine beneath miles and miles of solid ancient ice, a vast, dark, silent sea, a realm untouched by sunlight, yet potentially warmed enough to remain in a liquid state. This is a concept that truly expands our sense of what is possible in the frigid reaches of the outer solar system. The idea first gained significant traction in 2006, when a scientific paper was released in the journal Icarus. Icarus, for those unfamiliar, is a highly respected publication dedicated to solar system studies, a forum where new planetary theories are presented and rigorously debated among the scientific community. This paper, a product of careful analysis and bold hypothesizing, suggested that the slight anomalies observed in Rhea's gravitational field, combined with its composition, might be best explained by the presence of such a hidden layer of liquid water. It was a ripple in the scientific pond, a gentle perturbation in our understanding that hinted at something profound beneath the quiet exterior of this moon. Now it is crucial to understand that while this idea is profoundly intriguing, it is still highly speculative and not as well supported as the subsurface oceans on moons like Europa or Enceladus. Think of it as a quiet suggestion, a beautiful possibility, rather than a confirmed fact. Europa, Jupiter's famous moon, offers much stronger evidence. Its surface is crisscrossed by chaotic terrain, suggesting regions where the icy crust has broken and reformed over a liquid layer. More compelling still, Europa exhibits features that appear to be direct evidence of cryovolcanism, where plumes of water might erupt from its surface. Similarly, Saturn's own moon, Enceladus, is a star in this regard, actively spewing geysers of water ice and organic molecules into space from its south pole. These plumes, observed directly by Cassini, are almost universally accepted as direct proof of a large active subsurface ocean beneath Enceladus's relatively thin ice shell. Rhea, however, does not exhibit such dramatic direct evidence of active plumes or widespread geologically dynamic, chaotic terrain. Its surface, as we've explored, is ancient and heavily cratered, suggesting a much less active interior over recent geological time. This difference in observational evidence is why Rhea's potential ocean remains firmly in the realm of intriguing hypothesis, a whispered dream, rather than a clearly seen reality. Yet, even as a hypothesis, the presence of such an ocean would have significant implications for Rhea's potential habitability. Whenever scientists consider the possibility of life beyond Earth, the existence of liquid water is almost always at the top of the list of requirements. Water acts as a solvent, allowing chemical reactions to occur, facilitating the transport of nutrients, and providing an environment where complex molecules can form and interact. If Rhea harbors a secret liquid ocean beneath its icy shell, even if it's cold and dark, it would immediately elevate the moon's status from a mere frozen ball to a world with astrobiological potential. It means that somewhere even in this distant, frigid corner of the solar system, there might be a long-lived environment conducive to the very earliest, simplest forms of life. Imagine a hidden ecosystem entirely independent of sunlight, powered perhaps by subtle chemical reactions occurring at the interface of the water and a rocky core, or by geothermal vents similar to those found in the deepest, darkest parts of Earth's oceans. It's a profound what if, a quiet hope that beckons us to consider the universe's boundless capacity for fostering life. Furthermore, the existence of such an ocean would expand our understanding of the conditions necessary for liquid water to persist in the outer solar system. How could an ocean on Rhea remain liquid for billions of years, so far from the sun's warming rays? The internal heat source for such an ocean would likely be subtle. It could come from radioactive decay within Rhea's small rocky core, a gentle warmth emanating from the breakdown of unstable elements. Or it could be generated by tidal heating, the constant squeezing and stretching of the Moon by Saturn's immense gravity. While Rhea's orbit is not as eccentric elliptical as that of Enceladus, which experiences strong tidal flexing, even subtle tidal forces over eons could generate enough friction and heat to maintain a liquid layer, especially if the ice shell is a good insulator. This would challenge our current models of icy moon interiors, suggesting that even moons without dramatic geysers or obvious signs of active geology could still hold vast hidden reservoirs of liquid water. It would mean that the habitable zone for liquid water, and thus potentially for life, extends much further out into the cold, dark reaches of space than we previously dared to imagine. It truly opens up a universe of possibilities, a silent, vast potential waiting to be explored. The discussion around Rhea's potential ocean is a beautiful example of the scientific process in action. It begins with anomalies in data, a subtle hint that something might be amiss with our current understanding. Then a hypothesis is proposed, a bold idea that attempts to explain these anomalies. This hypothesis is then subjected to rigorous scrutiny, compared against all available evidence, and contrasted with more robust examples like Europa and Enceladus. Even if the direct evidence is not yet overwhelming, the possibility itself is enough to inspire further research, to guide future missions, and to keep the sense of wonder alive. It's a testament to the humility of science, acknowledging when we don't have all the answers, and embracing the beauty of the unknown. Related to these internal mysteries, and certainly puzzling to scientists, is Rhea's overall shape. As we discussed briefly, while many large moons and planets tend towards a perfect sphere, the most gravitationally efficient shape, Rhea is noticeably non-spherical. It's not perfectly round, but rather slightly flattened at the poles and bulges at the equator, a shape we formally call a triaxial ellipsoid. Imagine a perfectly round ball, and then imagine very gently pressing down on its top and bottom, causing it to flatten slightly, while simultaneously stretching it ever so slightly along one axis around its middle. This subtle distortion is a common outcome of rotation, where the centrifugal force at the equator causes a bulge. Our own Earth rotating on its axis is also an oblate spheroid, slightly wider at the equator than at the poles. What's strange, however, is that Rhea's shape doesn't quite match what we'd expect based on its rotation rate. Given how slowly it rotates, due to its synchronous lock with Saturn always presenting the same face to the giant, its equatorial bulge should be more modest, more symmetrical, a gentler curve. The observed discrepancy, this slight but persistent deviation from the expected shape, is what has truly captivated scientists. It suggests that something deeper within Rhea is influencing its form. This discrepancy has led scientists to propose that Rhea might have a non-uniform internal structure, where denser material is concentrated away from its center in subtle, unexpected ways. Imagine, for instance, that the mix of rock and ice within Rhea isn't as perfectly homogeneous as initially thought, or that there are subtle variations in density caused by ancient colossal impacts that subtly shifted its internal mass distribution. Or perhaps the formation process itself wasn't perfectly uniform. This suggests that the interior is not a simple perfectly blended slush, but rather holds subtle concentrations of heavier or lighter materials in unexpected places, creating a gravitational tug-of-war that manifests in its slightly distorted shape. It's like discovering that a seemingly simple bell doesn't ring quite true, prompting an investigation into its internal composition to find the subtle imbalances. This odd shape, this subtle imbalance, is a cosmic secret kept within Rhea's icy heart, hinting at complexities that current models struggle to fully explain. It pushes the boundaries of our understanding of how celestial bodies are truly formed, how they evolve over eons, and how their internal dynamics can subtly express themselves on their external form. It serves as a beautiful reminder that the universe, even in its quietest corners, holds profound mysteries that continue to inspire our wonder and deepen our humble inquiry. The shape of a moon, seemingly a simple physical attribute, can become a profound clue, a silent whisper about the powerful forces and hidden structures that lie beneath its tranquil surface. It's a puzzle that scientists continue to unravel, using the gentle precision of their instruments to measure every subtle deviation, every tiny variation, in the hope of painting an ever clearer picture of Rhea's true nature from its brightest surface to its deepest, most enigmatic core. As we conclude this contemplation of Rhea's interior, let these subtle mysteries settle in your mind like distant starlight, filtering through a veil of clouds, reminding you of the beauty in the unknown. Having drifted through the imagined depths of Rhea's icy interior and pondered the subtle hints of its hidden complexities, let us now gently turn our gaze to a pivotal chapter in its recent history, a time when humanity received its clearest, most intimate look at this distant moon. This chapter is dominated by the Cassini mission's close flybys, a series of breathtaking encounters that transformed Rhea from a distant fuzzy orb into a detailed world of ice craters and fascinating geological features. The Cassini spacecraft, a monumental undertaking, representing a joint project of NASA ESA and the Italian Space Agency, was truly a marvel of international collaboration and scientific ambition. For over a decade, from 2004 to 2017, Cassini diligently studied the entire Saturnian system. Imagine this spacecraft traveling billions of kilometers across the vast cold void of space, arriving at Saturn, and then performing an intricate, years-long dance among its rings and moons. It was a patient observer, a silent, tireless photographer and data collector, sending home a continuous stream of revelations that forever changed our understanding of this ringed jewel and its diverse family of satellites. Cassini didn't just fly by. It settled in becoming an adopted resident of the Saturnian system, observing the ebb and flow of its cosmic tides. Among its many targets, Rhea was a subject of particular interest, and Cassini executed several close encounters with this moon. These weren't mere distant glimpses. They were carefully planned audacious maneuvers, bringing the spacecraft within astonishing proximity to Rhea's frigid surface. The closest of these flybys occurred on the 11th of January 2011, a date now etched in the annals of planetary exploration. On that day, Cassini passed a mere 76 kilometers above Rhea's surface. To put this into perspective, imagine flying in an airplane just a few tens of kilometers above the ground. That's how close Cassini got, almost skimming the icy peaks of Rhea's landscape, close enough to feel the subtle gravitational tug of the moon itself. This was not a quick dash. The spacecraft carefully choreographed its approach to maximize data collection during this fleeting yet profound moment of intimacy with a distant world. Another significant close flyby, among others, occurred on the 9th of March 2013 when Cassini passed just 997 kilometers above Rhea's surface. While not as breathtakingly close as the 2011 encounter, this flyby still offered an unparalleled vantage point, allowing the spacecraft to gather further valuable data and continue its detailed mapping of the moon's surface. Each flyby was an opportunity, a precious window, to collect more pieces of the puzzle that is Rhea. These close approaches were not merely for the thrill of proximity. They were absolutely crucial, allowing the spacecraft to capture incredibly detailed images of Rhea's cratered terrain with a clarity never before seen. Imagine a world suddenly revealing its true face, its smallest imperfections and grandest features brought into sharp, astonishing focus. The cameras on Cassini were far superior to those on the Voyager probes, revealing textures, shadows, and subtle variations that had previously been mere blurs or entirely invisible. These images were like geological maps laid bare, allowing scientists to see the moon's history written in its very ground. Every ridge, every valley, every impact scar was suddenly rendered with exquisite precision, allowing for a level of geological analysis previously unimaginable. Beyond just stunning visuals, these flybys allowed Cassini to gather valuable data about the moon's composition. Its suite of instruments, including spectrometers, carefully analyzed the light reflected from Rhea's surface across different wavelengths. This allowed scientists to identify the specific elements and molecules present, confirming the widespread presence of water ice, but also detecting the subtle signatures of other materials, as we discussed previously. It was like taking a microscopic look at the moon's very building blocks, understanding not just what it looked like, but what it was truly made of deep down. Furthermore, these close passes were instrumental in helping scientists determine that Rhea does not have an internal magnetic field. This finding, while seemingly simple, carries significant implications. Many active planetary bodies like Earth generate magnetic fields through the motion of liquid metal in their cores. The absence of a strong intrinsic magnetic field on Rhea suggests that its interior, even if it contains a small rocky core, is not undergoing significant convection or harboring a large molten metallic core. This supports the idea of Rhea as a largely undifferentiated body, or at least one whose internal dynamics are far less energetic than larger, more complex worlds. It adds another piece to the puzzle of its formation and thermal history, suggesting a moon that cooled relatively quickly and remained mostly frozen throughout its long existence. These flybys truly provided us with our best look yet at Rhea's surface features. The landscape revealed by Cassini's sharp eyes was dominated by two distinct types of terrain, a contrast that had been first hinted at in the earlier, less detailed Voyager missions, but which Cassini brought into vivid focus. The first type, and perhaps the most widespread, were the heavily cratered regions. These vast expanses were pockmarked with an astonishing density of impact craters, some small, some colossal, overlapping and interweaving, to create a textured ancient tapestry. These heavily cratered areas are thought to be extremely old, possibly dating back to the early days of the solar system. Imagine the immense period of late, heavy bombardment, a time when the inner solar system was pelted by a relentless barrage of asteroids and comets, remnants of the violent planet-forming era. While this bombardment primarily affected the inner planets, its echoes would have been felt throughout the nascent solar system. Rhea, being a world that has largely remained cold and geologically quiet since its formation, preserved these ancient impacts like a meticulous historian. These ancient surfaces therefore provide an invaluable record of the intense bombardment that occurred in the solar system's youth. They are like the oldest pages of a cosmic diary, etched with the memory of a chaotic formative period, allowing scientists to piece together the history of impacts across different worlds and understand the dynamic environment in which our solar system truly came into being. Each crater here is a silent witness, a frozen moment from a time when worlds were still being violently shaped. In stark contrast to these ancient scarred regions were the younger, smoother plains. Imagine areas where the surface appears almost pristine, with far fewer craters, or where older craters seem to have been gently erased. These smoother plains are likely the result of a resurfacing event, a process that somehow covered up the older, more heavily cratered terrain. One prominent theory for this resurfacing is the ejection of material from large impact events. Picture a truly colossal asteroid or comet striking Rhea, perhaps the impact that formed Mammaldi, or another immense basin. The sheer energy of such an impact would not only create a massive crater, but would also blast out an enormous amount of material ice and pulverized rock into space, forming a massive ejecta blanket. This material would have fallen back to the surface over a wide area, acting like a cosmic blanket of snow. As this ejected material settled, it would have filled in older craters and created smoother regions, essentially burying the ancient scars beneath a fresh layer of material. It's a process of renewal, a cosmic reset button, where the violence of an impact, ironically, leads to the creation of pristine, untouched landscapes. The distinction between these two terrains offers profound insights into Rhea's geological evolution. The heavily cratered regions speak of an early passive history, a period of simply enduring the cosmic onslaught. The smoother plains, on the other hand, hint at moments of more dynamic activity, even if that activity was triggered by external impacts. They suggest that Rhea, despite its seemingly quiet demeanor, has undergone periods of dramatic transformation, its surface constantly being sculpted by both external forces from the cosmos and the subsequent internal or secondary processes these forces unleash. These images from Cassini allowed scientists to map these distinct terrains with unprecedented accuracy, revealing the subtle narrative of Rhea's geological timeline, a silent chronicle written across its icy face. The silent data flowing from Cassini during these flybys was like a treasure trove, each byte a new whisper from Rhea. The precise measurements of its gravitational field during these close approaches further refined our understanding of its internal mass distribution, helping to confirm, or at least strengthen, the idea of its largely undifferentiated interior. By carefully tracking the subtle tug that Rhea exerted on Cassini, scientists could infer how mass was distributed within the moon, whether it was concentrated in a dense core or spread more evenly throughout its icy and rocky composition. This was crucial for supporting the frozen dirty snowball model, providing direct gravitational evidence for its bulk composition. The entire mission was an exercise in patience and precision, turning distant light and faint gravitational signals into concrete knowledge about a world millions of miles away. As we gently float away from the detailed landscapes revealed by Cassini's close flybys, let us now contemplate perhaps one of the most intriguing results from the entire Cassini mission concerning Rhea, what it didn't find. Sometimes the absence of something can be as profound or even more perplexing than a grand discovery. This particular non-discovery added a layer of quiet mystery to Rhea's profile, a testament to the meticulousness of scientific inquiry and the subtle surprises the universe always holds. Prior to Cassini's arrival in the Saturnian system, some scientists had proposed that Rhea might have a system of rings. Imagine that. A moon itself orbiting a ringed giant might possess its own miniature set of cosmic hula hoops. This idea wasn't born from pure speculation. It was based on curious, albeit indirect evidence. The hypothesis stemmed from unusual measurements of electron densities around Rhea, made by Cassini in 2005. As Cassini orbited Saturn, its instruments were constantly monitoring the environment, including the density of charged particles like electrons. When the spacecraft observed dips in the electron density in the vicinity of Rhea, it was a subtle anomaly, a faint signal that caught the attention of researchers. Think of it like this: if a moon had a thin ring system, even one made of very sparse dust or tiny ice particles, those particles would interact with the charged electrons in Saturn's magnetosphere, potentially absorbing or scattering them. This interaction could in theory create regions of lower electron density, like faint shadows cast by invisible structures. So these electron density dips around Rhea were interpreted by some as a possible smoking gun for a nascent or very tenuous ring system, perhaps akin to the faint dust rings seen around Jupiter, or the incredibly tenuous rings of its moon Thebe. The idea was captivating a moon with rings, a nested cosmic beauty, a truly unique arrangement in our solar system. However, despite this intriguing initial hint, and armed with this very specific hypothesis, Cassini embarked on careful searches during its subsequent flybys. Imagine the spacecraft with its advanced cameras and particle detectors performing a diligent silent vigil, meticulously scanning the regions where these hypothetical rings might exist. Scientists commanded Cassini to orient its instruments specifically to look for the faint signature of ring particles, either through direct imaging of reflected sunlight or by observing how starlight might dim as it passed through a ring plane. They looked for the telltale scattering of light, the subtle gravitational perturbations, any definitive sign of these proposed structures. It was a search driven by both hope and scientific rigor, a quiet quest for a potential cosmic marvel, but perhaps to the quiet disappointment of some, and certainly to the reevaluation of the initial hypothesis, Cassini found no evidence of rings around Rhea. Imagine the careful analysis of every image, every data point, only to find no definitive signature, no clear confirmation of what the electron density measurements had suggested. The rings, if they existed, remained stubbornly invisible to Cassini's powerful gaze. This was a non-detection, a silent negation of a captivating idea. This non-detection doesn't completely rule out the possibility of some kind of debris disk around Rhea, but it does make it much less likely. Perhaps the electron density dips were caused by something else entirely. A transient phenomenon, a temporary interaction with Saturn's magnetosphere, or some other complex process not directly related to a permanent ring system. It might be that any debris around Rhea is so incredibly sparse, so diffuse, or so small that it simply falls below Cassini's detection limits. Or perhaps, if a ring system did briefly form in Rhea's distant past, it quickly dispersed or fell back onto the moon's surface, leaving no lasting trace for Cassini to observe. It's a subtle reminder that the universe can present us with tantalizing clues that lead to unexpected conclusions, constantly challenging our interpretations and pushing us to refine our understanding. The absence of evidence is not always the evidence of absence, but in this case, for a moon that was thoroughly scrutinized, it points strongly towards no substantial ring system. Now let us turn our attention to another intriguing aspect of Rhea, its place in Saturn's complex system of moons. Saturn is not just a planet with rings. It's a bustling gravitational metropolis, a vast cosmic family of diverse worlds. Rhea orbits Saturn in what is known as the E-ring, a unique and diffuse ring of ice particles. Unlike Saturn's main dense rings that are made up of countless individual ice particles locked in tight flat orbits, the E-ring is a much broader, fainter, and more vertical structure, almost like a donut of icy dust encircling the planet at a significant distance. What makes the E-ring particularly fascinating and directly relevant to Rhea is its origin. This diffuse ring of ice particles is thought to be supplied by the cryovolcanic eruptions from Enceladus. Enceladus, another one of Saturn's moons, is a marvel of the solar system. Famous for its active geysers, plumes of water ice, and organic molecules erupting from cracks in its south pole. Imagine tiny frozen fountains constantly spraying material into space. This material, propelled by internal heat and pressure, escapes Enceladus's gravity and disperses into orbit around Saturn, gradually forming the vast, shimmering expanse of the E-ring. So the E-ring is not a static structure. It's constantly being replenished by its active inner neighbor Enceladus, a testament to the dynamic interconnectedness of Saturn's moon system. While Rhea itself doesn't seem to be geologically active like Enceladus, meaning it doesn't have its own active geysers or significant internal heat driving surface changes in the present day, its position in this ring means it's constantly interacting with these ice particles. Rhea orbits within the extremities of the E-ring, beyond where it is densest. Imagine Rhea as a quiet boat sailing through a very fine mist. Although the mist, the E-ring particles, is extremely thin at Rhea's distance, it is still there. Over immense periods of time, this constant gentle interaction with the tiny ice particles of the E-ring could subtly affect Rhea's surface properties. How might this interaction manifest? The continuous, albeit gentle bombardment by E-ring particles could contribute to Rhea's incredibly bright appearance. These particles are pristine, freshly ejected ice from Enceladus. As they gently rain down on Rhea's surface, they might act like a constant microscopic recoding, replenishing its surface with fresh, reflective ice. This could help to maintain Rhea's high albedo, preventing it from gradually darkening over geological time due to the accumulation of micrometeorite dust or space weathering from solar radiation and charged particles. It's a fascinating idea. Rhea's very brightness, its dazzling reflective quality, might in part be a gift from its more active sibling Enceladus, a silent, ongoing exchange of cosmic material. This intricate relationship between Rhea and the E-ring, and by extension with Enceladus, paints a vivid picture of the interconnectedness of the Saturnian system. These moons are not isolated worlds. They are part of a vast, dynamic gravitational family influencing each other in subtle, yet profound ways. The activity on one moon can create environments that affect others, even those millions of kilometers away. It's a grand cosmic ballet where each dancer influences the steps of the others, creating a complex and ever-evolving choreography. The fact that Cassini meticulously searched for rings around Rhea and found none closing one intriguing chapter, while simultaneously revealing Rhea's subtle interaction with the E-ring opening another, speaks volumes about the nature of scientific exploration. It is a process of proposing, testing, refuting, and re-evaluating, a constant dance of curiosity and discovery. Even the negative results, the things we don't find, provide crucial information narrowing down the possibilities and guiding us towards a more accurate understanding of the universe. So, as we contemplate Rhea's place in this grand cosmic design, let us hold in our minds the image of this bright ancient moon, silently orbiting its giant parent, bathed in the faint glow of Saturn, and gently interacting with the icy remnants of a distant active sibling. It's a world that has surprised us with its presence, puzzled us with its form, and now reveals the subtle intricacies of its cosmic neighborhood. Rhea stands as a testament to the fact that even in the vast expanse of space, everything is subtly connected. A silent, beautiful symphony of gravitational and particulate interactions that weave the fabric of our solar system. As our gentle voyage to Rhea draws to a close, let us reflect on the quiet wonders we have encountered and the profound questions that still linger like distant stars in the vast cosmic night. It's clear that this moon, often overshadowed by its more famous siblings, like the hazy methane-rich Titan or the geyser-spouting Enceladus, is a fascinating world in its own right. Rhea may not boast the same dramatic activity, but it holds a unique charm, a quiet dignity that invites a different kind of contemplation, a deep appreciation for the subtle intricacies of planetary evolution. It is a world that has patiently waited for its story to be told, for its quiet mysteries to be acknowledged. We have journeyed across its heavily cratered hemisphere, a testament to the brutal yet formative barrage of the early solar system. Each impact a silent chisel shaping its ancient face. We've then drifted to its relatively smooth side, hinting at moments of resurfacing. Perhaps by cosmic snowfalls of ejecta from colossal impacts, a gentle renewal of its icy skin. We've breathed in our imaginations, its tenuous atmosphere, a whisper-thin exosphere of oxygen and carbon dioxide, a testament to the unexpected chemistry that can unfold even in the near vacuum of space. We've considered its internal structure, a seemingly homogeneous mix of rock and ice, yet holding the intriguing, albeit speculative possibility of a hidden liquid ocean. And finally, we've understood its place in Saturn's complex system of moons, bathed in the light of the giant and subtly interacting with the icy particles of the E-ring, a cosmic dance of silent influence. From its ancient scars to its ethereal breath, Rhea continues to intrigue scientists and spark our imagination, beckoning us to ponder the countless untold stories in the universe. But our exploration of Rhea is far from over. Indeed, for all that we have gently uncovered, many questions remain unanswered, floating like unmoored dreams in the cosmic ether. What is the exact nature of its interior structure? While models suggest a largely undifferentiated mix, could there be subtle layers or pockets of material that we simply haven't detected yet? How has it evolved over the billions of years since its formation? What were the precise conditions that led to its current state, from its icy composition to its peculiar triaxial ellipsoid shape? These are not mere academic queries. They are invitations to delve deeper, to seek out the subtle clues that will complete Rhea's long, quiet narrative. Perhaps the most captivating question of all, the one that whispers through the vastness of space and touches upon our deepest hopes, is: could it harbor simple forms of life in a hypothetical subsurface ocean? If such a hidden sea truly exists, warmed by some subtle energy source and teeming with the organic molecules already detected on Rhea's surface, then the possibility, however remote, of microbial life cannot be entirely dismissed. It's a profound thought, a secret world of life thriving in perpetual darkness beneath miles of ice, a testament to life's incredible adaptability and the universe's boundless capacity for surprise. These questions and many more await future missions to the Saturnian system. For it is only through continued exploration that we can hope to find the answers. While there are currently no planned missions specifically targeting Rhea, the Moon is likely to be observed by any future spacecraft sent to study Saturn and its moons, just as Cassini followed in the footsteps of Voyager. Future probes will undoubtedly carry even more advanced instruments capable of peering deeper, sensing more subtly, and perhaps finally confirming or refuting the existence of Rhea's hidden ocean. Imagine a new generation of robotic explorers gently descending towards Rhea, carrying radar instruments that could probe beneath its icy shell, or even tiny submarines capable of melting through the ice to explore a dark liquid world below. The dream of exploration never truly ends. It merely rests, waiting for the right moment, the right technological leap to awaken once more. As we conclude our journey to Rhea for tonight, let's take a moment to appreciate the incredible diversity of worlds in our solar system. Each celestial body, from the familiar planets to the most distant tiny moons, is a unique masterpiece, a testament to the countless ways matter and energy can combine and evolve. From the scorching sulfuric surface of Venus, shrouded in its dense, toxic atmosphere, to the icy plains of Pluto, a distant, lonely world at the edge of our known solar system, each offers a distinct lesson in planetary evolution. From the towering volcanoes of Mars, silent giants on a rusty red landscape, to the potential subsurface oceans of icy moons like Enceladus, and perhaps even Rhea, bubbling with the promise of unseen life, our cosmic neighborhood is filled with wonders waiting to be explored, waiting to inspire our awe. Rhea, with its icy surface reflecting the distant sunlight, like a diamond in the dark, stands as a testament to the beauty and mystery of our universe. It reminds us that even in the seemingly silent, uninhabited corners, there is profound complexity, hidden depths, and stories waiting patiently to be told. It's a world that invites us to slow down, to observe, to wonder, and to accept that not all answers are immediately apparent. The universe is a grand book, and we are but gentle readers, turning its pages one by one, content to marvel at each unfolding chapter, even if we do not yet comprehend the entire story. As we continue to explore and learn, who knows what secrets this distant moon may yet reveal. Perhaps one day a future mission will confirm a hidden ocean or detect the faint chemical signatures of life, forever changing our place in the cosmos. Or perhaps its enduring mystery will be its greatest gift, a perpetual invitation to dream and to wonder about the silent, vast potential of the universe. Well, that's all we have time for today on our gentle voyage to the Saturnian moon Rhea. I hope you've enjoyed listening to this quiet journey of discovery, allowing your mind to drift through distant realms and contemplate the profound beauty of the cosmos. If you've enjoyed what you've heard, please feel free to follow us for more podcasts on other fascinating space topics, where we'll continue to explore the wonders of our universe with a gentle spirit of inquiry. But for now, I'm Alex McCohen, and this has been Astrum. All the best, and see you next time. May your dreams be filled with starlight and silent icy worlds.